Today we are going to start a new chapter which is on current transformer and potential transformer. They are called CT and PT in short. What is a current transformer or what is a potential transformer? So, as the name suggests, these are basically transformers, just transformer. Now, what is a transformer? So, a transformer, an ideal transformer basically has a magnetic core and we have a couple of coils, two coils wound on top of it, and now if we apply a voltage, alternating voltage AC in one of the coils and call this voltage as V1, then we know that a voltage is induced in the other coil, which we call the secondary coil. If this is the primary coil, then this is the secondary coil, and here we will get some voltage. So, if we connect a voltmeter, then we will have a voltage detected by this voltmeter, and we know that if the number of turns for the primary is N1 and the number of turns for of the secondary coil is N2, then and if we call this voltage induced in the secondary is V2, then we know that the relationship V1 by V2 is equal to N1 by N2. This is true for an ideal transformer. Okay. And also, if the current that is flowing in the primary coil is I1 and if any current I2 flows here in the secondary, then the relationship between I1 and I2 is given by it is the opposite N2 by N1. Here we had V1 by V2 equal to Ny by N2. Here I1 by I2 is N2 by N1, opposite, or you may write this as this is what happens in an ideal transformer. Okay. So, this is the property of an ideal transformer. And we will call an transformer or an instrument as an ideal transformer only if these two relations are satisfied, true, perfectly true. Okay. Then only we will call that transformer as an ideal transformer. But practical transformers, you may already know that they do not obey this relationship perfectly. They deviate from this relationship somehow, somewhat, and that is practical transformer, where this is not exactly true. Okay. Now, let us start with an ideal transformer only. So, and how can we use this transformer for measurement? Say we want to measure a very high voltage, very high AC voltage, of course, say maybe around 10 kV, 10 kilovolt, but we have voltmeters we have a voltmeter which can measure up to say 10 volt maybe, okay. And so can we use this voltmeter to measure 10 kilovolt? No, not directly. Why? Because firstly the voltmeter itself may get damaged immediately as soon as we connect this 10 volt voltmeter to a 10 kilovolt source. If we connect it this way, the voltmeter may get damaged immediately because of this high voltage applied across it. So, a high current will flow and it may get damaged immediately. That is one thing. Even if it is not damaged, then you know that the maximum reading can be only 10 volt. So, pointer can never indicate 10 kilovolt. Okay. So, this is not possible. So, this is not possible to measure in this way. Now, what can we do? We can use a transformer to step down this voltage to a lower voltage, okay, and then we can measure it. So, what we can do? So, this is the source which is 10 kilovolt. Let us connect this to a transformer, okay. And the symbol of a transformer is often like this, you know. So, this is the schematic: primary with N1 turns, secondary with N2 turns, and if I draw these lines between them, which means it is a iron core transformer. Okay. So, what we can do? We connect this to a transformer, step down transformer, where N1 and N2 are the number of turns for primary and secondary, with N1 by N2 is equal to say 1000. And here we will connect the voltmeter. Its range is 0 to 10 volt. Okay. So, this voltage is 10 kilovolt, but this transformer is a 1000:1 transformer. So, the voltage 10 kilovolt will be stepped down by a factor of 1000. So, it will 10 kilovolt will become just 10 volt, okay, from this relationship. So, if this voltage is V2, this voltage is V1, V1 is 10 kilovolt, then V2 will be V1 multiplied by N2 by N1, okay, and now N2 by N1 is 1 over 1000. So, this is 10 kilovolt by 1000 is 10 volt. So, this way we can measure a large voltage, a huge voltage with a ordinary range voltmeter, okay. And then this transformer, which is just a transformer, will be called as a potential transformer or PT. The function of this potential transformer is to bring down this this high voltage to a smaller range which we can measure easily. Okay, so PT, potential transformer, brings down, normally brings down, never I mean we generally do not need PT to increase the voltage. So PT brings down a high voltage to a measurable value, suitable lower value. That's what a potential transformer does. Now, so now we know what a PT is. Now let's see what a current transformer is. Once again, say I have a transmission line like this, where say 1 kiloampere current is flowing. Now I want to measure this current. What we normally do? We normally have to open this circuit, insert an ammeter in series with this line, and then this ammeter will indicate the current. Now say I have an ammeter with range 0 to 1 ampere, but we want to measure a current about 1 kiloampere. So what can we do? We cannot connect this ampere which has a range of 0 to 1 ampere like this, because immediately then this ammeter will burn. Such a huge current will flow through it, it will get damaged in no time. So this is a wrong circuit. Okay. Now what we can do? What we can do is this: if this is the transmission line, we will open it and connect a transformer here. The primary side of the transformer will be connected like this, and the secondary side we will connect it to this ammeter. Zero to 1 ampere ammeter. And now if we choose this ratio N1 by N2, primary number of turns and secondary number of turns, such that N1 by N2 is equal to 1 over 1000, then if this current is 1 kiloampere, okay, then that means 1 kiloampere current is flowing here. The current that will flow in this circuit I2, this is I1. Okay. So we can write I1 N1 equal to I2 N2. So I2 will be I1 N1 by N2. So this is I1 is 1 kiloampere and N1 by N2 is 1 over 1000. So this is just 1 ampere, which we can measure with this ammeter. So this circuit is fine. We can use this circuit to measure a huge current. Okay. And then this transformer we call this a current transformer, and the function of the current transformer is to bring down a high current to a measurable low value. That is the function, main function of the current transformer is. Okay. Now, there are other functions as well. We will talk about them soon. But before that, you may ask a question that why can we not use a suitable shunt resistance to bypass current and measure large current in this way. Okay. So, that is also a possible way. So, if I want to measure a huge current like this one, so I have around 1 kilo ampere current. So, what I can do, I connect an ammeter whose range is 0 to 1 ampere to this, and we put a suitable shunt resistance, a small resistance, okay, such that most of the current get bypassed through this shunt resistance. That is also possible. So, you may ask, why should we not use this scheme instead of using a current transformer? What are the relative advantage and disadvantage? Okay. So, let us take an example to understand this. What is the merit of using a current transformer? Say for example, the internal resistance of this ammeter is 99.9 ohm. Okay. This is just an example. Okay. Say this is the internal resistance. Now, let us ask what should be the value of Rs, so that we can measure 1 kilo ampere with this arrangement. Okay. So, now here these two together forms the measuring instrument. So, this is the current measuring instrument, which is composed of a 1 ampere ammeter with a suitable shunt resistance, and the value of the shunt resistance should be, how can we compute this? So, we want that if this current is 1 kilo ampere, only 1 ampere current will flow through the ammeter. So, this current here will be 1 ampere and remaining current will go through the shunt. So, this value will be this is 1000 ampere, this is 1 ampere. So, we will have 999 ampere current flowing through the shunt. Okay. Now, from this we can write 1 ampere, which is the current through the ammeter, multiplied by this resistance 99.9 ohm, which is the ammeter resistance, okay, or meter resistance. This should be equal to the voltage across these two terminals, which is same as the voltage across these two terminals. So, we can write this as Rs multiplied by the current through the Rs, which is 999 ampere, and then Rs will come out to be 99.9 divided by 999. So this is uh, 0.1 ohm. Right? So RS will be 0.1 ohm. Okay, and if we choose RS to be so, then this will be my measuring instrument which will measure this current. Okay, fine. Now let's estimate two quantities. Number one, how much is the power consumed by this measuring instrument. Okay, so the power consumed by the measuring instrument will be how much? It will be this voltage multiplied by the current. If I call this voltage as V, okay, so power will be same as the product of V and this current, assuming these are RMS values. This is RMS value. By default, in case of AC, this is RMS. Okay, and this is resistive, so power factor is 1. So there, I mean, this is resistive, this is also resistive, so power factor is 1. So we can write the power to be equal to V multiplied by 1 kiloampere current. And now how much is V? V is 1 ampere multiplied by 99.9 ohm. This is V multiplied by 1 kiloampere. Okay, so then this is equal to 99.9 times 1000 watt, or we can write it as 99.9 kilowatt. This is a huge power being consumed. Okay, then also let us ask another question: how much is the internal impedance or resistance of the measuring instrument? That means this thing together, this ammeter and the shunt resistance. What is the internal resistance of this combined thing? So this is nothing but parallel combination of RS and this meter resistance. So this will be equal to 99.9 parallel, this is 0.1 ohm. Okay, so this value will come out to be 99.9 multiplied by 0.1 divided by 99.9 plus 0.1 ohm. This is equal to, so this is this is 100 and this is 9.99. 9.99 by 100 ohm, which is 99.9 milliohm. Okay, so these are the two values. Okay, now let us compare this with the scenario where we are using this current transformer. Okay, so if we use this current transformer, Then once again let us ask how much is the power consumed. Okay. Now the power consumed, so this is an ideal transformer. Okay. So this is an, assume the transformer to be ideal. So there is no loss at all in the transformer. Okay. So and practically no transformer is ideal, so there will be some loss, but since the transformer loss is very generally very low, transformers are highly efficient instruments, so we can ignore for to get a rough idea about the power consumed. So power will be equal to, so no power is lost in the transformer, the power is lost only in the ammeter, and the ammeter resistance is 99.9 ohm, and the current flowing through this I2 is equal to, as we calculated before, this is 1 ampere. Okay. I2 is equal to 1 ampere, we have calculated this before. So power will be power loss in ammeter only, which is same as 1 ampere multiplied by I square R. Okay. So or multiplied by this voltage. So the voltage will be 99.9 ohm multiplied by 1 ampere. This is I square R, and this is 99.9 watt. Okay. So let's compare this with the power consumed by this arrangement, which was 99.9 kilowatt. Here it is only 99.9 watt. Okay. So much less than the power consumed by the shunt arrangement. Now let's ask the other question. What is the internal impedance of the measuring instrument? Now which is my measuring instrument? My measuring instrument is this transformer together with this ammeter. So I can say that these two things together is my measuring instrument. The current enters through this and leaves through this. Okay. So how much is the internal impedance between these two terminals? Terminal call this AB. Okay. So impedance between A and B, or resistance between this will be how much? So that will be this voltage that will appear between A and B, VAB, divided by the current, okay, that is flowing from A to B, which is 1 kiloampere. Now how much is VAB? Okay, let's find VAB. To find VAB, let us first find the voltage across the ammeter. Okay, so we can write this, say VAB divided by voltage across ammeter, this will be nothing but equal to N1 by N2 which is 1 over 1000, and this implies VAB will be voltage across ammeter divided by 1000, and voltage across ammeter is nothing but equal to this current which is flowing here, 1 ampere multiplied by this resistance 99.9 ohm. So this is 1 ampere multiplied by 99.9 ohm whole divided by 1000. So this is VAB. Okay, so this is equal to 99.9 by 1000 volt, and from this from this we can write this internal resistance as VAB by 1 kilo ampere, which is now VAB is this 99.9 by 1000, and this is 1 kilo ampere, so another 1000 volt by ampere. So this is 99.9 into 10 to the power minus 6 ohm. Okay, so this is from here. So you see this resistance is very small. Okay, so observe, resistance is very small. And much smaller compared to this arrangement where we had 99.9 milliohm, but here it is 99.9 microohm. So this internal resistance is much smaller, and when measuring an current with any instrument, we want the instrument to have small internal resistance, right? So ammeters we want to have ideally 0 resistance. Lower the resistance, it's better, because then there will be less voltage drop across the meter or measuring instrument. So the original current will not change much. And here we see, if we use a CT current transformer, then the arrangement, then the measuring instrument has much smaller internal impedance compared to a shunt scheme. And we also have seen the power loss in the measuring instrument is also much smaller. So these are some advantages of using a current transformer instead of a shunt resistance. Okay, so these are the advantages of some of the advantages of a current transformer. Okay, so let's write advantages of CT. Number 1, less power loss. Number 2, lower internal impedance, or which we can write as lower burden voltage. What is burden voltage? We have defined this. Burden voltage is nothing but the voltage drop across the meter. Voltage drop across the measuring instrument. Of course, the first advantage, or you call it the 0th advantage, is range changing, which we already have said. If we want to measure a high current with a normal ammeter, we have to bring down the current to a measurable value. So that's the first use, of course. Another point I will okay, so these are some of the advantages we have seen so far. Okay, fine. Now the of course obvious fact is that CT can be used only for AC circuits, AC currents, because transformers do not work with DC at all. So, for DC circuits we cannot have a current transformer. And okay, so now let us do a similar analysis with potential transformer. Okay, so let us do the analysis of potential transformer PT versus series resistance. Okay, let me before that mention another small advantage, which is about CT. So, with CT, so this is how we use current transformer. The ammeter is connected across the secondary of this transformer. So, therefore, if you want to change this ammeter due to any reason, you do not have to operate with this 1 kiloampere line. You can do everything on the secondary side. If we had the ammeter connected directly in this 1 kiloampere line, and if we want to replace it, we have to disconnect this power supply and this current line, then have to insert a new ammeter, which we do not need here. Okay, and also so let us write that easy to insert or replace in meters, since the meters are connected only across this secondary of the transformer. The main line is not touched at all. And also one more thing you should know, that current transformer can also be used not to connect only ammeter. We can connect relay and other protective equipments also in the power system. What is a relay? What is the function of a relay or a circuit breaker? Say, the function of a circuit breaker is to realize whether the current level is going beyond acceptable level. If it goes there, then the circuit breaker and the relay will switch off the power supply. It is a safety instrument. Okay, but this circuit breaker is in a sense also a measuring instrument. Why? Because it is measuring the level of current, whether the level of current is going beyond the safe level or acceptable level or not. It may not display you the number on a screen or with a pointer saying how much the current is, but it is essentially sensing the current, measuring the current, and if the current goes beyond a level, then it does something, it stops the current. So, circuit breakers, relays, they are also in a sense some measuring instrument, and you can actually connect such relays, such circuit breakers also across the secondary of this current transformer. Not just meters which give you indication with pointer how much the current is, but also protective instruments. So, let us also write relay, circuit breaker, etc. Relay, circuit breaker, etc. can also be connected across the secondary of a city. So, you can connect actually multiple things together. Okay. So, it is possible that you connect it this way. So, if this is the power line, then let this be the primary of primary side of the city. You may connect multiple equipments like an ammeter, which will display you the current. You may connect, say, a relay or circuit breaker, all across the secondary of the city. So, this is the city. Okay. Now, let us come to PT. So, we will do first an small analysis, a comparison between PT versus series resistance. So, let me take the example I had here. So, I want to measure a 10 kilovolt voltage and I have a 10 volt voltmeter. Okay. So, to measure 10 kilovolt with 10 volt voltmeter, we have two choices. One is use a potential transformer, a step down transformer, and then this voltmeter. This is one choice. This is 10 kilovolt and its range is 0 to 10 volt. Another choice is connect a very high resistance with the voltmeter this is 10 kilovolt of course and measure it. So, you have two choices. Okay. Now, we will ask the two questions of course. One is how much is the power loss, okay. So, for this let us assume the internal impedance or resistance of this voltmeter is let us take it to be 1 kilo 1 kilo ohm. Okay. Okay. So, this is 1 kilo ohm, this has a resistance of 1 kilo ohm. Okay. So, we are taking a high value because voltmeter should have, we know voltmeter should have high internal impedance. Okay. One small thing is that the numbers that I am taking is mainly for ease of calculation, mainly for ease of demonstration. Practical numbers may differ a bit from this example. Okay. So, how much is the power loss here? That will be only the power loss in the voltmeter, because we can assume that this PT is ideal. So, no drop no loss occurs here. Okay. So, this PT is an ideal PT. So, the loss occurs only in the voltmeter. Then the loss is V square R, which is same as the 1 kilo ohm. Okay. So, this is 1 kilo ohm, 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 the voltage across this voltmeter, and this voltage is 1 volt, because we have taken 1000:1 PT. So if this is 10 volt. Okay. So this is 10 volt only. So we can write 10 square multiplied by 1000 ohm watt. So this is equal to 100 kilowatt. Huge amount. Now how much will be the sorry, there is a mistake. The mistake is, this is V square by R. So this is 100 by 1000 is 0.1. Okay, and here power loss is how much? This will be this voltage 10 kilovolt square divided by these two resistances Rs plus 1 kilo ohm. Now how much should be Rs? Let's calculate that first. Rs should be, okay, so this voltage here to here is 10 kilovolt. This is 10 kilovolt, but between these 2 points the voltage should be only 10 volt, because the voltmeter can measure only up to 10 volt. So the voltage here to here should be 10,000 minus 10. Call it VR. Okay. So VR is equal to 10,000, 10 kilo minus 10 volt. Okay, and so how much should be Rs? So we can write that VR divided by Rs, which is this current, should be same as 10 volt divided by this resistance 1 kilo ohm, because this is also the same current, and from this we write Rs is equal to VR divided by VR multiplied by 1 kilo or 1000. Okay, VR multiplied by 1000 divided by 10 volt. So this is equal to, now VR is 10,000 minus 10, so the value will be multiplied by 100 ohm. So that's a huge one. Okay. Now let's put this value. Okay, so this is becoming 10,000 multiplied by 100. So this is 100. This is 10,000 into 1000. So 1000 minus 1000. Okay, so here we can write 10 kilo square divided by Rs plus 1 kilo ohm, which is this, minus 1000 and plus 1 kilo ohm. This cancels. So we have 10 to the power 8 divided by 10 to the power 6 watt. So this is 100 watt. Okay, so this power loss is much greater than this power loss. So with a PT, the power loss is much smaller than if we have a multiplier or series resistance. Now let's ask the other question: how much is the internal resistance of this scheme? Internal resistance. So internal resistance means the resistance of this measuring instrument. So this together is the measuring instrument. Voltage measuring instrument. Now what is the internal resistance as seen between these 2 points A and B? So this is equal to resistance between A and B, that you can write as, say, if this current is I and this voltage is 10 kilovolt, so you can write this as the voltage by current 10 kilovolt divided by the current I. Now how much will be this current I? So for that, okay, let's call it I1. So this is I1, and let's call this current as I2. How much is I2? I2 is 10 volt divided by 1 kilo ohm. Volt divided by 1 kilo ohm. So this is 10 milliampere. 10 milliampere, and then this I1 will be, so we know I1 by I1 N1 is equal to I2 N2. From that, I1 will be I2 N2 by N1. Now I2 is 10 milliampere and N2 by N1 is 1 by 1000. Okay, so this is I1, and therefore internal resistance from this we write 10 kilovolt by I1, 10,000 volt by I1 is 10 milliampere, so divided by 1000, and then this becomes equal to 10,000 multiplied by 1000 or okay, and this milli, okay, this milli we can convert this by another 1000. So we have into 100 into 1000. So this is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the power 9 ohm. Huge. And in this case, how much is the internal impedance? So this is now my measuring instrument. Voltmeter in series with RS. So internal impedance is equal to Rs plus 1 kilo ohm meter resistance. So which is, from here you can write 10 to the, this is the value actually 10 to the power 6, 1 2 3 4 5 6, 10 to the power 6 ohm. So this is 10 to the power 6, but this is 10 to the power 9, this is much larger. Okay. So the advantages of PT we can write firstly, it brings down the voltage to a measurable value, measurable range. Secondly, less power loss compared to series resistance, offers higher internal impedance, and we know voltage measuring instruments or voltmeters should have infinite or as large as possible internal impedance, offers higher internal impedance. Therefore, less current is drawn from the circuit and the original voltage is not changed much. And then what else? Okay, we can also write that it is safer for the operating personnel, because if somebody wants to connect a voltmeter directly to this 10 kilovolt, is much dangerous than connecting a voltmeter or disconnecting a voltmeter to this 10 volt side. So this is safer. And you can also connect, like in the case of CT, you can also connect other equipments like circuit breakers, relay, like in this case a over voltage relay or something to this PT. So you can also connect relay or circuit breaker at the secondary. Okay, so like this. So if this is an unknown voltage we want to measure, so we can connect it to a step down PT transformer, and then here we can connect the voltmeter which will indicate the voltage. We can connect relay, circuit breaker, whatever we want, other instruments like this. Now the last thing we will discuss in this class is how to measure power using CT and PT. In a large voltage, large current circuit. Okay, say I have a circuit like this. So this is a huge voltage, this is a high voltage which is feeding this load, and this current is also very high, a high current. This current is also very high, and we want to measure, say, the power being delivered by the source or consumed by the load. So what do we normally do? So we do use a wattmeter, or if we want to measure energy, then we use a energy meter. Okay. So we use a wattmeter or energy meter. Which will have two coils, one to sense the voltage, another to sense the current. Okay. So call one of them as the current coil CC, another as the potential coil PC, voltage coil. Now what we do? We normally connect the current coil in series like this, and we connect the voltage coil. So we may connect it this side or also this side, ignoring the small power loss in current coil or in pressure coil, which we discussed before in much detail. So ignoring that small error, this is how we connect. Okay. And now the problem is this current is a high current, and if this is a normal wattmeter which cannot allow high current, then what can we do? Instead of connecting this current directly to the current coil, we will use a current transformer. So let us put a current transformer. So this is CT, and therefore this current that flows here will be stepped down to a low value, and we can connect it to the wattmeter. Similarly, if we cannot measure this voltage directly because this is a high voltage, what we can do? We will disconnect it from here and connect a potential transformer, which is a step down transformer. This is PT, and then we will connect the secondary side to the pressure coil of the wattmeter. So that's how to do it. So simple. Now that's so simple, but if you are interested, I will just give you some thought exercise for you. Think of yourself. For example, how to connect a compensated wattmeter. If you recall, a compensated wattmeter is a wattmeter where we have an additional coil, compensation coil, which goes over the current coil in opposite direction. So you recall that, and that the function of that compensating coil is to eliminate the small error due to the loss in pressure coil or in current coil. Okay. So in this diagram, we have ignored that small error. We have taken that to be negligible. Now think, if we do not want to ignore that, and if we have a compensated wattmeter, how to connect it. Okay. So if you draw the circuit diagram, you can post it in the forum. We will see it. I will be very happy if you try this. This is one question. Then also think about the plus minus sign of or the direction how to connect this current coil and the put pressure coil, because the reading may come out to be negative. Okay, so think about how to connect the wattmeter considering the negative, possible negative reading. So by this I mean, if you have say this plus minus signs, I mean not here, okay, so on if you have plus minus signs on the wattmeter on the two coils, then which is the correct diagram to measure the load power or the power supplied by the source. So think of it, that will be very interesting thought exercise. In our next class we will talk about errors or non-idealities that CT and PT, current transformer and potential transformers, may have, because today we have assumed the transformers are all ideal, where the relationship V1 by V2 is equal to N1 by N2 is absolutely correct, and N1 I1 equal to N2 I2 is absolutely correct, but that is not true in practice. So what could be the effect and how to take care, etc., we will discuss in the next class. Thank you.